Hello, ladies and gentlemen. Tonight we're going to be talking about parent functions, and we have some objectives. So the objectives are going to be able to identify 7 parent functions by graph or by an equation. 2, to be able to create a graph representation of the parent function, and 3, to be able to create an equation representation of the parent function. So parent function definition is, a parent function is the simplest form of a particular type of function. And so we'll see what we mean about that in just a second. So here are the parent functions that we need to know. We have linear, reciprocal, the absolute value, cubic, square root, quadratic, and exponential. So let's first look at a linear function. We have the function f of x equals x, or also, oops. Alright, so f of x equals x, or basically y equals x. So if I put in a negative 4, what do I get out? Well, negative 4. If I put in negative 2, I get a negative 2, 0, 0, 2, 2. And I think there's supposed to be a 4. Oh, there it goes, a 4. That was stirred. And 4. Alright, so if we were to plot this here, 2, 3, 4, 1, 2, 3, 4. So we've got a point here, 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 so on and so forth. Alright, so we could see that we have a straight line. That's how you can tell it is a linear function, is that it's a straight line. It is the only function that is just a straight line. So that should be pretty easy to distinguish. Now let's look at some examples of some linear functions. So temperature conversion. This is going from degrees centigrade to Fahrenheit. Sorry, from Fahrenheit to centigrade. Exchange rates. This is the current exchange rate for dollars to euros. Or even if you have a cell phone bill, for example, this one right here, C of M equals 25.25 M plus 50. So what this would represent is, say if your monthly fee is $50, $50, and for, say, maybe your first 500 minutes, and then every minute you go over, you get charged 25 cents. So if you spoke of 501 minutes, your bill would be $50.25, and so on and so forth. Alright, the reciprocal function. The reciprocal function is exactly just what it sounds like. So if we have a fraction 2/3, 2/3, we know that its reciprocal is what? 3 over 2. Just like y equals x, the reciprocal is f of x equals 1 over x. So let's look at what this function does. So if I put in negative 2, I get 1 over negative 2, so I get a negative 1/2. So I'm at negative 2, negative 1/2. At negative 1, I get 1 over negative 1, which is just negative 1, right there. And at negative 1/2, I get 1 over negative 1/2, which is actually a negative 2. And then at 0, I put 1 at 0. And now what do we know about 1 over 0? We can't divide by 0, right? So this is actually cannot happen. We have an asymptote here. We'll get more into that later. But we just know that one of our rules is that we cannot ever divide by 0. So we know on that part of the graph, we should never have a value there. Now if I put in 0.5, 1 over 0.5 is 2. At 1, I get 1 over 1, which is 1. And at 2, I get 1 over 2, which is 1/2. So if I were to continue filling this graph out, it would actually look, let me see if I could do this kind of neatly. So it gets closer and closer that way. and then it kind of goes like this. And then same thing on this way. It goes, hey, that was much better. Boom. Alright, so then our graph looks like that. The reciprocal graph. Know it. Now we see the reciprocal graph. Extremity dominance is balanced through a reciprocal function, like left arm moves with your right leg and vice versa. So think about when you walk, opposite arms, opposite legs. And then again, exchange rates. If I have the euro as a function of a dollar, then I could vice versa that and make it the reciprocal function. Absolute value function. Now, we already know what absolute value function does, right? Most of us know that it changes negatives to positives, or everything makes everything positive. It also measures the distance from zero. Now, the way to tell the absolute value function, let me find my little pin. Oh, here we go. Come on, pin. There we go. So, it has the bars, right? So, even if I'm looking at something like f of x equals absolute value of 2x plus 1 absolute value, these are my absolute values, minus 3, we can always tell the absolute value function because of its absolute value bars. So that should be a pretty much easy one to always get, right? And let's see what the absolute value does. If I plug in a negative 4, well, negative 4 turns positive, so I get a positive 4. A negative 2 turns positive 2. A 0 is still 0. 2 is still positive 2. And 4 is still 4. So if I'm here at negative 4, and we can see, what do we get here? A V. Which you could also think of the V in value. Absolute value, you get a V for your graph. And you can't mess up the equation because they have the bars up and down. Going on. Alright, here's some examples of the absolute value function. You know, you're talking about you go 3 blocks east, 6 blocks west, 11 blocks east again. You can ask two questions. Where are you relative to where you started? So the direction counts, right? So you need to keep that sign. But if you just ask, how far did you go? Well, now you just add up the amount of blocks that you did despite the direction, so you can drop the sign and just give the distance is what you need, right? Another example is, suppose you're driving a car. Going too fast is obviously a hazard and might earn a speeding ticket. Going too slow is also a hazard and can earn a ticket as well. What matters is how different one speed is from everyone else, from what everyone else is doing. So to explain this, like, we'll look at a graph. Now say this is the optimal speed right here. So if you're going this speed, you're putting yourself at 0 risk. So that's the optimal speed. Now as you start to increase your speed, your chance of risk, whether it being an accident or getting a ticket, increases. Same thing, if you decrease your speed, you have a bigger chance of also still getting pulled over because going too slow is unsafe, as well as causing an accident. So you could see how that is a absolute value function. Alright, on to the cubic function. F of x equals x to the third power. Now, we could look at this and tell how it's going to be a cubic function from another function because, oops, here we go again. Alright, pen, got it. Alright, because, well, it's cubed, right? If you have x to the third power and no other power higher than it, then it's going to be a cubic function. Now, let's see what happens when we plug our numbers into our cubic function. If I plug in a negative 4, I get negative 4 cubed, which is a negative 64. Now, on here, my negative 4 is, I'm going to be way down there. Way down there. Alright, so let's see where we're at for negative 2. Negative 2 cubed, well, we're at negative 8. So we're right here. So this actually, this this is going to be coming. Okay, we'll do that in a second. 0. At 0, well, 0 cubed is 0. 2 cubed will be positive 8. And 4 cubed will be 64. So this is going to be much steeper than what it's showing. And then it comes up like this. Not 2 right by oops. Well, keep on. At 2, we're at 8, and then it keeps going up like that. The distinct look that this graph has is like that. And you can see that there. So it's the only one that does that. It should be pretty easy to recognize on a graph. Yeah. And so examples of this. So imagine that. Oh, shoots. I need something that always writes a pen. All right. So you wind a propeller of a toy rubber band airplane. So, and the rubber band winds around itself. Suddenly, the entire band will twist into a spiral. So, when it does that, what you have, so now you have this rubber band, and you wind it up. When you let it go, it starts to spin really quickly, and then at a certain point, it stops, right? And then it unwinds the other way. That's your cubic function. It is patterned after that. And then here are some other examples of the cubic function. Now square root. We all know what the square root function is. I'm going to get my pen now so I don't mess it up. It has a square root, right? If it has a square root in the equation, it is a square root function. Pretty self-explanatory, right? Now, let's look at what happens when we put some of our numbers into a square root function. I think this was supposed to be negative 9, and I think that was supposed to be negative 4. All right. So let's look what happens when we put our numbers in. So negative 4. What do we know about a square root? Right? We cannot have anything negative in it. So once again, just like we had a 0 earlier, we're going to put, because we can't have any negatives there, whether it's a negative 9 or a negative 4. Now 0, if we put 0 in, we still get 0 out. If we put 4 in, we get 2 out and 3. So we see what we get here for our graph is 0. At 4, I'm at 2 right here. And then way down here at 9, not up here. So we get this gradual, like, to where it kind of starts to go like that. That's the square root graph. Here's also the square root graph. Real life definition of square root. Alright, you also see it a lot with Pythagorean theorem. You see it, I mean, it is used in so many countless applications in engineering, architecture, physics. I mean, anything to do with parabolas, you're going to use it. And okay, I'm going on to quadratics. So quadratics we've seen before. We know that the distinction in this graph is going to be, in this equation is going to be what? The squared, right? If it has a squared and nothing higher than it, it is quadratic. And what happens when we plug our numbers in here? Negative 4 squared is positive 16. Negative 2 squared is positive 4. 0 squared is 0. 2 is 4. And 4 is 16. 2, 3, 4. We're going to be way up here somewhere. At negative 2. 4. Something like that. So what we get is we get this kind of, it's supposed to be a little bit more of a U shape. Sorry, the pen I'm using isn't exactly the best pen. Alright, but yes, it is more of a, that was a little bit better. Something like that. U shape. And these are also seen, I mean, any sports pretty much that involves a ball in the air, throwing a ball. Fire missile, throw a stone, it'll go up and come back down, and, you know,